Hi guys, today I would like to discuss the continuity concept to electric field lines. Just recall what is electric field. An electric field is a property of space. The property is that it puts a force on charge. So if you take a charge, so in this vicinity of the charge, electric field exists. So because of the electric field only, force will be applied on the other charges. Let us see what we discussed. Suppose if you take this positive charge as a source charge, this is the source charge. And at P you want to find the electric field. Further, just bring a test charge of plus Q. So to find out the electric field at point P, we need to bring a test charge. So a test charge of plus Q. So it's a compulsory. So that is the convention we are following. Since it's a plus charge and source charge also a positive, a force will be acts above since they both repel each other. Now that's the force direction gives the electric field direction. So this is the convention what we are following in this case. Now the electric field direction in this case equal to the force direction. So these two directions are the same. So this is the convention what we are following. To find out the magnitude of the electric field at this point, we are using a formula. The magnitude of electric field equal to force per unit charge. So here the force per unit charge. So this is the unit charge what you kept at here. And the force, that force is a Coulomb force. Notice at here this electric field is a vector and the force is also a vector. The SI unit is Newton per Coulomb. Since force units are Newton and charge unit is Coulomb. Newton per Coulomb is the force. Now if you take precisely the electric field directions, if source charge is a positive, so for that, as we discussed it here, bring a positive test charge. On the positive test charge, what is the force? So there is a force direction. So in the same force direction, the electric field direction also will be exist in the same direction. That is the convention what we are following. Suppose if we take a negative source charge, in this case the source charge is negative but the test charge is positive. We cannot change the test charge because it's the convention what we are following. Since it is a positive and source charge is a negative, the force will be acts downwards because the positive wants to attract negative. So in this case the force direction and electric field direction, they both are the same. Now these are the two differences for the positive source charge and for the negative source charge. Note that electric field E in the vicinity of negative charge minus Q towards the charge, the direction that plus Q test charge would move. So by taking this concept, today I would like to extend the same concept. That concept leads how to draw the electric field lines. The concept of electric field lines gives the visual representation of the electric field strength. So we need not depends upon the mathematical formula or the mathematical dependence. The visual representations of the electric field, which is given by Michael Faraday, which help us to how to find the strength of the electric field. So this we can understand with the help of the electric field lines. First of all, what is electric field lines? So electric field lines are imaginary lines. They are imaginary, hypothetical. Imaginary lines drawn in such a way that the direction at any point is the same the direction of the field at that point. So take an example. Suppose this is the positive source charge, and if I bring a test charge of the positive, if I bring a test charge of positive at here, positive test charge. Now at here the positive test charge experience a force in this direction. Now if we keep this positive test charge anywhere in this vicinity, then it experiences the same force, depends upon the position. Now the imaginary lines which you draw from the source charge, so these lines are known as electric field lines. So that electric field lines gives the visual representation about the electric field. Suppose if we keep a negative source charge, and here if I keep a positive test charge, so this positive test charge wants to attract according to convention. So this direction, force direction, electric field directions are the same. So we will represent for the negative source charge, the electric field lines are towards to the source charge. But for the positive test charge, the electric field lines move away from the source charge. See the NCERT diagram. At here, if the charge Q is greater than 0, now the lines which they draw, these are the moving away. Greater than 0 means it's the positive. So from your positive source charge, the electric field lines are moving away. If it is a negative, Q less than 0 means negative. If the charge is negative, the electric field lines are coming towards to the charge. Finally, electric field lines go away from positive charge and towards negative charges. So this is the convention we are the following to represent the electric field lines. So let us see at here much more visualize. Suppose I am having a bunch of negative charges. To show the electric field lines in this vicinity, I need to bring a test charge. So this positive small charge is my test charge and this negative charge is my source charge. Now where is the force? Now the force direction, since it is the positive, the force direction towards to the negative. This is the force direction, but I want to represent the electric field directions. According to conventions, the electric field lines are moving towards to the source charge, because the force direction and electric field direction both are the same. So the field lines are in the direction of force, that would put a positive test charge. If you are having a source charge, whichever the type is. To know the electric field lines, you need to bring a positive test charge. On the positive test charge, in which direction force exerts, in that direction only the electric field lines exist from the source charge. Let us see another. Now, here I am having a source charge positive. To know the electric field lines, I need to bring one more positive source charge. Now, according to this, field lines are in the direction of force. First, let me find out where is the force direction. Now, the force direction is moving away because they both are the positive charges, so they will repel each other. So, the force direction is moving away. Again, field lines are in the direction of force that would put on a positive charge. Now, you need to draw electric field lines to this source charge. So, you have to draw the field lines in the direction of the force. It means the field lines are moving away. So, in a simple manner, the electric field lines for a positive source charge moving away from the source charge. If it is a negative, it's coming towards from the source charge. So, these are the two single charges or mono charges. Let us guess. What is the direction of field lines around the unknown charge? So, this is my unknown charge. Try to find out the direction of field lines. So, here they are given a help of, this is a test charge and this is along the force direction. Now, in this case, the test charge is not positive. The test charge is not positive. Can you guess? Yeah, it will be the opposite what I discussed in the earlier case. Now, this is the force direction. Since it is a negative, now the electric field lines is moving away. Now, can you guess what is the nature of the source charge? Yes, it's obviously positive because electric field lines move away from the positive charge. Let us take another case. So, this is the exact visual representations or practical diagrams. So, here a small bunch of lines. So, these all are electric field lines. How did they draw? So, we have to do with an experiment with the help of iron filings. If you sprinkle iron filings around this charge, so the iron filings will be attract, depends upon the nature of the charges. So, if it is a negative, those all will be coming towards. That is the convention. But if it is a positive, the electric field lines are going away from the positive charge. So, let us discuss some more examples of multiple charges. Suppose if you take two charges at a distance, one is positive and one is negative. So, the electric field lines starts from the positive charge and they will end in the negative charge. So, that's why here the field lines as drawn from the positive to negative. They are the starting from the positive charge and they are ending at the negative charge. So, everywhere the electric field lines will be there. Suppose if you take both are the same charges. If the both are the same charges, there is no case that so they will interact each other. So positive charge and positive charge gets repel each other, so the electric field lines moving away from them. So if charges are opposite, so this is the pattern of the electric field lines. If the charges are identical, either the plus or minus, this is the pattern of the electric field lines. Let us see some more examples. So this is the experimental result for the same if the charges are the opposite. Here you can see clearly the iron filings are aligned in the direction of electric field lines. Suppose if I draw the same by visualizing the positive to the negative charges, that will be represents the nature of these charges. These are the non-identical charges. One is the plus, another one is minus. Suppose if we take similar charges, identical charges, here you can see the electric field lines pattern. Since it's not yet clear, but still we can able to understand they are not at all interacting. They are moving away from each other. So these electric field lines never interact each other. So this is the pattern of the electric field lines we can get if they both are the identical. Similarly, if they both are the negative charges, the direction of the electric fields only changes, but they never interact each other. So let's see another case. Suppose here you can see it's both are the different charge plates. One is the positive charge, another one is the negative charge. So this is the very important case we can discuss in the capacitors. So one is exactly the positively charged plate, another one is negatively charged plates. In between here you can see the electric field lines are straight. So there is the electric field lines pattern between the two oppositely charged plates. So this is the exact visual representation of the two oppositely charged. Here you notice that the number of field lines tells about the electric field strength. So we can study after this the electric field lines properties. In their properties we can understand. So here you can see at the 3 points, at these 3 points, at here and at here and at here, the electric field strength at here, by observing the arrow mark you can understand, and the electric field strength at here by observing the arrow mark at there, and the electric field strength right at here. Just notice the arrow mark that tells about its direction and the strength of the electric field. And we know that electric field is inversely proportional to distance. So if the distance is more, the electric field strength is less. Now you can guess where the electric field strength is more. Now, let us take different electric field patterns for objects of unequal amount of charges. Suppose if we take unequal amount of the charges, here you can see at here the electric field lines are the more. It means you can guess at here electric charge is not the same of at there. So how did I know that? So that point we can understand by seeing the electric field lines. There you observe the number of the electric field lines are more. If the charge quantity is more, obviously the electric field strength is more. So depends upon the charge quantity, we need to represent the electric field lines. If the charge is the more, electric field strength is the more. So these are the 4 different examples for the unequal amount of charges. I would like to represent the electric field with the help of PHET stimulation. So this stimulation helps us to visualize the electric field more. So I am having it here positive charge and the negative charge. Suppose if I take a positive charge at there. Now here you can see in this space the electric field lines, the arrow marks are representing the electric field lines. Since it is a positive charge, the electric field lines move away from the positive charge. And here the strength of the electric field is represents the intensity of the arrow mark. So if you can go at the right this corner, the arrow mark intensity is less, it means the electric field strength is less. But when you come close to this positive charge, so the arrow mark intensity is more, it means its lighting is more, brightness is more. So obviously the electric field strength is more. Or with the help of test charge, so here it is my test charge. If we can place a positive test charge, so the strength of the electric field at this particular point shows at here the length of the arrow mark along with the direction. Suppose if I move it away from the source charge, automatically the electric field decreases because it's a 1 over r square. So that's why the electric field strength is decreases. Suppose if I increase the quantity of charge, now I am adding 1 more nanocoulomb, total together 2 nanocoulombs. So by adding 2 nanocoulombs, here you can see the strength of the electric field is increased. If you can place a test charge there you can understand. Suppose you can put 1 more, now it's the 3 nanocoulombs, the strength of the electric field increases. So like that. Now if I take negative charge, if it is a negative charge, the electric field comes towards to the negative charge. Now they appears to come from infinity towards to the negative charge. Now if I bring a positive test charge, here my sensor is a positive test charge, its direction also shows towards to the electric field direction. This tells to me the strength of the electric field at this right there and the direction of the force. Now I would like to do with the 2 oppositely charges. I would like to see what is the electric field line pattern. Yeah, here you can see the electric field lines are now they are started. If you can take this arrow mark and it is appears to end at here, and if you can go above, it is starting up to there and it is ending at there. So now like that, each one it is just forming just like loop. So that's exactly what we have seen in the diagram. Now if you take both oppositely charges, now if I take both oppositely charges, that is a positive, another one is a positive. Here you can see the electric field lines are not interacting from the positive to negative, so they are moving away from the both of the positive charges, since they both are the same charges. So this is the way to draw the electric field line patterns. And if you take same, both are the negative charges. If you take both are the negative charges, this is the same the electric field line patterns. But now the direction of the electric field lines will be changes. Now they are coming all the way from infinity and ending at negative charges. So electric field lines gives the visual representation how the electric field will be exert a force in the vicinity of the source charges. NCERT having 4 diagrams. So this is the electric field lines due to oppositely charged, and this is the electric field line patterns due to same charges, and above that, and this is the electric field lines due to negative charge, and first one, it is the electric field lines due to positive charges. So please practice all 4 diagrams carefully. Try to draw the electric field lines. Now let us see some general properties of these electric field lines. The first one, the field lines start from positive charge and end at negative charges. So in the 4th diagram, we can understand the electric field lines are starting from positive charge and ending at negative charge. So this happens if you are having more than one oppositely charges. If there is a single charge, they may start or end at infinity. So in this case, if you can take, this is a single charge, that is also negative. For the negative charge, this electric field line starting at infinity, and for this positive charge, electric field lines are starting from at here, and where they are ending? They are ending at infinity. So that is electric field lines properties. And second point, in a charge free region, electric field lines can be taken to be continuous curves without any breaks. So in a charge free region, so at here, so this is the charge free region. So at here, the electric field lines we should take as a curves, and that curve should not be discontinuous. And third point, two field lines can never cross each other. So this point is very important point. Electric field lines, they never cross each other. What happens if they cross each other? If they cross each other, it means there is a point of intersection. The problem with electric field is it's a vector. If there is a point of intersection is there, at that point two directions will be there. So that is not possible at the same place two electric field directions. That's the impossible case. So that's why the electric field lines can never cross each other. They never cross each other. They all are individual lines. And fourth point, and very important point, electric field lines do not form closed loops. So why they do not form closed loops? So that explanations we can understand in the coming chapter. But right now I can skip this point by giving as an granted electric field lines, they do not form closed loops. because if they form closed loops, we cannot able to find out the precise where its exact direction is. Okay, so these are the very important points regarding the electric field lines properties.